So guys, starting again, I know that you completed part of a homework assignment. And just by way of sort of refreshing our memories, guys, the questions that you were able to answer in homework were relative to electrolytes, non-electrolytes, strong electrolytes, weak electrolytes. So guys, what I don't want to do is I don't want to answer questions about the homework. We're going to talk about the homework as one big assignment on Thursday. But what I am willing to do, if you'd like, is relative to those narrow group of topics. Again, non-electrolytes, electrolytes, strong electrolytes, weak electrolytes. Is there anything there generally that you want to talk about before we move forward? Please.
Why would you classify like electrolytes? I don't know, like I get that it's solubility stuff, but
Yeah, Jeanette, that's a really good question. And not only, did you hear Jeanette's question? Forgive me, I'm going to paraphrase, but it was basically, why do we even care to classify these things as strong electrolytes, weak electrolytes, non-electrolytes? Guys, the root of that question is even more important than the question itself. Because Jeanette, what you're trying to do is you're trying to make sense of this, right? How does this fit in the bigger context? How are we going to be leveraging these things down the road? And that's a great way to be thinking. But guys, let me answer that question specific to this particular content. So why do we care if something's a strong electrolyte, a weak, or a non-electrolyte? And the answer for now is because we care about how these things behave in water. And what you're about to, so let's remind ourselves. Guys, let's do this and then you'll see. So guys, non-electrolytes, make your brain go to non-electrolytes. And guys, when your brain goes to non-electrolytes, what is the physical example of a non-electrolyte that you can hang on to? Sugar. So let your brain go to sugar. That is our example of a non-electrolyte. Do non-electrolytes dissolve in water? Yes, they do dissolve in water. But what do they not do in water? Ionize, dissociate, same term. So guys, so when we see sugar dissolving in water, we see the sugar molecules going into water, but they're not themselves breaking apart. Yes? That's a great question, and let's talk about it. So guys, this is why we do what we do when we grade homework, because guys, it's after you've done the homework that you have all these wonderful questions. So guys, why does sugar not break into ions? Think about it this way. You've heard this, right? If you have a chain and you pull on it, where does the chain break? The weakest link. You've heard that, right? Chains break at the weakest link. Well, guys, out of there. This is sugar. And guys, I know that it's a little bit hard to see probably on my screen, but let me zoom in and maybe you can. So let me be able to draw as well. Just a second. Oh boy, I really screwed up. Just a moment. I need this. Okay, now I can go back here, do this, do this, do this, go back here and get the water out of there. Okay, so now let me do this while I can draw. So here, Jessica, is the answer to your question. Why does sugar not ionize? And guys, the reason is because just like a chain, things break at their weakest point. So let's talk about what's holding this together. So guys, this represents a sugar molecule. It's actually carbon, 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 hydrogens, oxygens all around it, but we just represent it like that. What forces hold that molecule together? Not IMFs. Inside the molecule, what is it that holds a sugar molecule together? And guys, if you aren't sure, let me go, because this is important you understand this. So let me zoom out, let me escape, let me go here. Let me pull up a sugar molecule. So sugar molecule. So guys, this is what that sugar molecule looks like. The purples are carbons, the reds are oxygens, the whites are hydrogens. That is what a table sugar molecule looks like. What are the forces that hold that thing together? What kind of bonds? Covalent bonds. And guys, covalent bonds are very, very strong. So I'm about to go back to the video that I showed you a moment ago. And now in your brain, each one of those like hot dogs that said C12H22O11, each one of those hot dogs is actually this. So guys, with that in mind, going back over to this, and then doing this, and then doing this, and then doing this, and then doing this. So guys, what are the forces that holds each one of those molecules together? Covalent bonds, and those are strong. Now let's do this. What are the forces between the molecules that hold them together as a crystal? Intermolecular forces. And what do we know about intermolecular forces? They're weak. And so guys, when sugars are attacked by water, so let's bring in the water. So now these water molecules come in here, and these water molecules just start latching a hold of stuff. And when they pull, where's it going to break? The weakest link. And what is weaker, intermolecular forces or covalent bonds? The intermolecular forces, and the intermolecular forces break, and the molecules get hauled off as whole molecules. And guys, I know there are questions, just a second. Contrast that with this. Now we're putting salt into water. And guys, what are the forces that hold the salt together? Ionic bonds. And guys, while ionic bonds are relatively strong, not as strong as covalent bonds, but while they are relatively strong, there are no intermolecular forces. So the only place this can break is for the ionic bonds to break, and either they will or they won't. If they do break, what do we call that salt? Soluble. What if they don't break? It's insoluble. But guys, if they're going to break, they have to break as ions because there's nowhere else for them to fall apart. Jessica, go ahead. Just a second, Mark. Go ahead. Not in water. Water isn't strong enough to break the covalent bonds. Let me say that differently. The attraction between water and the sugar molecules is not strong enough to break the covalent bonds. Can you get it to happen? Yeah, but you've got to add way more energy. So you could ionize sugars into carbons, hydrogens, and oxygens. It just takes more energy. Yeah? Is an ionically bonded substance. This is important though. So yes, salts are always ionically bonded, but what things create ionically bonded salts? It's either metals and nonmetals with a nonmetal, or a metal with a polyatomic, like sulfate, nitrate, those things. Okay, is that okay? Okay. Mark, just a second. Let's go ladies first. Go ahead.
I was just going to say, if you did get sugar to something, would it conduct electricity?
Yes. Yeah, and let's talk about that. Guys, we sort of skirted this issue. Let's talk. What has to be true of a substance? There's two things. What has to be true of a substance in order for it to conduct electricity? It's two things. Give me one. Has to have charged particles. What's the other thing? Those charged particles have got to be free to move. And so, guys, if you have a beaker of salt, this is just table salt. If you have a beaker of salt, will this conduct electricity? It will not. Are there charged particles in here? Yeah, sodiums and chlorides. Why doesn't it conduct? They can't move. Dissolving them in water frees them up to move. So it has to be both. It's got to be charged particles that can move, and then it'll conduct. Is that okay? Mark, go ahead. Yeah, so this is interesting. And if at any point this doesn't make sense, ask questions. All acids are molecules. So for example, if you've got HCl, that bond that exists between the hydrogen and the chloride is covalent. But when it breaks into ions. So all acids, whether it's strong or weak, all acids are molecular. They contain covalent bonds. Again, it's weird, but when they break, they create ions. But then the question becomes, what is the difference between a strong acid and a weak acid functionally? And again, we're going to talk about this in February, but we can touch on it quickly right now. So the difference between strong acids and weak acids. If you have a strong acid like HCl, it breaks into hydrogen and chloride ion. Here's the trick. Chloride does not have the ability to bond with hydrogen ions. So this cannot bond with this, therefore it doesn't go backwards, therefore it completely breaks apart. Something like vinegar, which is a weak acid, also breaks into protons and it breaks into acetate ions. Now here's the trick. Acetate actually does have the ability to grab a hold of protons, hydrogen ions. And when it does, it drives the reaction in the other direction, just a moment, and it reaches equilibrium, making it weak. So what's the difference between a strong acid and a weak acid? And the answer is these. These are what are called conjugate bases. And the conjugate base of a strong acid can't grab protons. The conjugate base of a weak acid can grab protons, pushing the equilibrium backwards.
Okay, and then how do you tell the difference between a weak acid and just like
Yeah, and the answer is you don't need to be able to do that right now. And we can talk about it then, but understand we're not going to really nitpick this to death right now. In March or February, we're going to talk about all those little details. Yeah, go ahead.
So if HCl and HCl don't bond, how do they end up together?
Yeah, and the answer is they didn't form this way. No, there are other reactions that can form the hydrogen chloride molecule, but you can't form hydrogen chloride in the presence of water by doing this. Because remember, this is in water, right? But if you took hydrochloric acid and boiled it, besides being really stupid and you'd probably die, but if you took hydrochloric acid and boiled it and got the water to go away, then the hydrogens and the chlorides can come back together. But that's not the way they make it. But understand, this is always in the presence of water. Is that okay? So guys, now back to Jeanette's question. Believe it or not, this is all going somewhere. So Jeanette asked the question, why do we care about strong, weak, electrolytes, non-electrolytes? And the answer is because we really need to know how these substances behave in water. It's important for us to understand when compounds or salts, when compounds go into water, do they dissolve? If they do dissolve, what do they do in water? Because guys, that determines the chemistry that they can carry out in water. So our understandings of if and how they dissolve will then inform the types of chemistry that they can do once they're in water. And so it's helpful for us to know the general ideas so we can predict how they'll behave. Is that okay? Other things you want to talk about in review? Justin.
How do you know how a compound dissociates? How do you know what it's going to split into?
Yeah, so good question. And so the answer is this. If it's a molecule, if it contains covalent bonds, it will not break apart. It will not ionize. If it's a salt, it'll break into a positive ion and a negative ion. And with something like HCl, that's pretty straightforward. It's just one of each of these. If it's an acid, it will break into a proton and then whatever's left. The only one that's a little tricky is what if you have something that is a salt that has a polyatomic anion like sodium nitrate. That's why you were to have memorized the polyatomic ions, because you could look at this and go, this is sodium and this is nitrate, and it'll split into sodium and then that polyatomic nitrate ion.
So what if that has like 3?
It won't. Yeah, you don't need to worry about that. We'll deal with simple cases. You don't need to worry about it. You guys okay? We okay? Okay. So guys, let me explain to you then where we're headed now. We've had big conversations about electrolytes, strong electrolytes, weak electrolytes, non-electrolytes. Now what we're going to do is we're going to bring this together, and this is exactly where Jeanette's question was leading us. We're going to bring this together and we're going to talk about the so whats. Okay, now that we know what these things do, how do they behave in water when they start mixing together? And we're going to talk about precipitation reactions. We're going to talk about acid-base reactions. We're going to talk about electrochemical redox reactions. Then we're going to spend a really quick day talking about titration, and then you're going to have your first test. So guys, we have 4 more days of class. A day on precipitation now, then a day on acids, bases, then a day on redox, then a day on titration, and then your test. So guys, what you're going to do with me in your notes is you are going to pick up where we left off, and we are going to go here, and what is going on? I don't want that video to play. Stop, move. Oh, that's really weird. I lost all my slides. Okay, so we are here. So guys, what we're going to do now is we're going to pick up this ball, so to speak, and I need all of these things. And we are now going to talk about precipitation reactions. We're going to define some terms, and then we're going to start drawing some pictures together, and you're going to learn something, well, very important, but I'll bring your attention to it when we get there. Okay, so guys, precipitation reactions. So let's remind ourselves, you learned this last year. What is a precipitant? It's a solid. Where does it come from? 2 reactions, 2 reactants. Where do those reactants have to be? In water. And when you react them together, they trade partners. What do we call those kinds of reactions? Double displacement. And one of the products that forms is not water soluble, and it becomes a solid. Is that all coming back to you? That's called precipitation. So guys, for what you need, the idea is this. A precipitation reaction, seems stupid, is a reaction that forms a precipitant. A precipitant, by definition, is an insoluble product of a chemical reaction. Most of these reactions are double displacement reactions. Well, that's a little redundant. Write down what you need. But guys, double displacement reactions are a double trading of partners. Well, I mean, we've said 3 times that one of the products isn't soluble, so we can probably clean that up. So maybe we leave it there. You guys know that we have the best male and the best female mountain biker in the school, in this room? Oh yeah. And I'm not either one of them. Jeanette and Nathan had a really good weekend riding their bikes. So guys, here then becomes the trick, and we're going to talk briefly about this, but we are going to talk. In order for you to make sense of this, you've got to understand when things dissolve in water. That's sort of an obvious connection, right? If a precipitate is a solid that doesn't dissolve, in order for you to figure out which the precipitants are, you need to know what does and does not dissolve in water, which would be a really good time, please do this, to grab your summary. Was it 4.2? Which table was it? Whatever. Guys, grab your summaries of table 4 point whatever it was. Was it on page 121? I don't even know. Grab them. So I think it was Mark and I that talked about this last time. But let's talk about this again. Guys, you're going to have to get comfortable with the idea in this class of damage control. You cannot learn everything. So you need to start going through the purposeful process of saying to yourself, am I capable of memorizing or learning this? Or is this beyond my capability and something I'm just going to have to get comfortable with getting wrong? And guys, every single one of you are going to have different thresholds in terms of where those boundaries lie. I shared this with you last time. I do not have a photographic memory. I really struggle memorizing things, except for the lyrics to songs from the 80s. I don't know why I can't get those out of my head, but that's stuff I wish I could just get rid of. Anyway, so guys, I really struggle with memorizing stuff. So I have just made myself comfortable with the idea that I'm never going to know all of table 4.1. That's just beyond me. So I've come to terms with the idea that I'm going to get the big ideas. I'm a big idea guy. And so I'm going to get the big ideas, and I'm not going to choke on the gnats while I'm swatting at camels, or vice versa. So, guys, you've got to decide. Are you a detail person and you're going to memorize every little bitty bit? Or are you a big idea person and you're going to memorize the big ideas with the understanding you're going to get some of these wrong? And that's up to you. But if nothing else, I'd like to know what were the trends, what were the things that you saw in that table that are going to help you be able to predict what things dissolve and what things don't. So what were some of the, and guys, please, as we talk about these, feel free to write down other people's ideas. So in general, Justin, what did you see? Yeah, ammonium. And guys, this is what I did, is I actually just created a column that says stuff that always dissolves. Seriously. And I put ammonium in that column because ammonium salts always dissolve in water. And guys, understand, always is a strong term. When you get married, never with your spouse in an argument use the words always and never. Because the minute you say always or never, if your spouse can come up with one negative example, they beat you. You never take out the trash. Well, I did take out the trash once about 3 years ago, and now you're the liar because they did it once. You know what I'm saying? Guys, never say always or never, because the minute you do, you've painted yourself into a corner because one negative example of what you just said proves you wrong. So, be careful with always and never. So what word do we use instead of always and never? Tends to. Seriously. Use this on the AP test. Ammonium-containing salts tend to dissolve. What other things tend to dissolve? Say it again. What? Acetates tend to dissolve. What else? Yeah, nitrates tend to dissolve. What else? Chlorides, bromides, and fluorides, which together are the halogens. So it's iodide, bromide, chloride, fluoride. So the halogen-containing salts tend to dissolve. But guys, honestly, this is one point where I sprinkle in the exception because I can keep track of this. Silver, lead, and mercury. Silver, lead, and mercury tend to be the exceptions to some of these solubility rules. So if I see a salt that has silver, lead, or mercury in it, my brain tends to go doesn't dissolve. So now if you want to create a doesn't dissolve column, I would put silver, lead, and mercury in that column because those salts tend not to dissolve. So what else do you got in either column? What about sulfates? Do or don't? They tend to dissolve. Now guys, you'll notice that the exceptions to the sulfate rules are not the same as the exceptions to the halogen rules, but there are exceptions to the sulfate rules. And I'll be honest with you, I don't know what they are. But what I do know is that there are exceptions to the sulfate always dissolving rule. So if I see sulfate, it makes me nervous. And I just look at it more carefully to see if there's something contextual that will clue me in. But if I see acetate, I just go, that always dissolves. Or if I see ammonium, it always dissolves. What else do you guys know? What's that? Good. So the group 1 salts always dissolve. Anything with lithium, sodium, potassium, rubidium, cesium, those always dissolve. What else?
And sometimes the calcium.
Yeah, heavy group 2. Calcium, strontium, and barium salts also tend to dissolve. So I summarize that by saying the group 1s and heavy group 2s tend to dissolve. Did we already mention nitrate? Nitrates tend to dissolve. What else?
Why don't the last two on both of one why aren't they included in the
Oh, francium and radium? Because they're so radioactive that we don't include them as our list of salts because their radioactivity makes them not good candidates to be components of salts. No, they stick around long enough, but we don't really mess with them in lab because they're very radioactive. They're deadly. What else, y'all? Other summary statements? Okay, that's fine. So with that said then, as our working understanding of solubility, guys, let's look at what precipitation looks like, and then we're going to start fiddling around with this together. So guys, just to give us a general sense, precipitation in a nutshell.
The first precipitate will be produced from aqueous silver nitrate and aqueous sodium chloride.
So guys, let's take a look. Sodium chloride, how do we know NaCl dissolves in water? Because we're not idiots. We know salt dissolves in water. But then guys, what about silver nitrate? How do we know that dissolves in water? It's a nitrate. But guys, when we see silver, that should make us nervous. Because silver is an exception. So we know something's coming. Uh-oh. So now,
Aqueous sodium chloride is added to the silver nitrate solution. We observe a white precipitate of silver chloride. This heavy precipitate thickens and falls to the bottom of the test tube as more.
So guys, how do we know that that's the silver chloride? Well, what's the other product? Sodium nitrate. And what do we know about the nitrates? That's always soluble. There are no exceptions to the nitrate rules. So by the process of deduction, we could figure out that that's the silver chloride because nitrates always dissolve. It's chlorine, chloride, that has an exception. So just by the process of elimination, even if we don't remember the details, we can figure that out.
Aqueous sodium chloride is added to the silver nitrate solution.
Okay, we get the idea. Good night. Stop.
This is a white precipitate of silver chloride. Again, we take...
Okay, so now we've got a different combination. Now we've got sodium iodide in silver nitrate. Yeah, right? Because we know nitrates are always soluble. Oh, here's another halogen. And now we're going, we don't just know the chloride rule, we know a halogen rule, which also includes iodide. And our rule is the halogen-containing salts tend to dissolve, but there are some exceptions. Silver, lead, and mercury. And so when these mix together...
This time we are going to add aqueous sodium iodide. When the sodium iodide is added to the silver nitrate, we get a pale yellow precipitate of...
And what is our precipitate? Silver iodide. Good.
Silver
Just like
iodide. Note that this precipitate is not the same color as white silver chloride. It is very pale yellow or cream colored.
You get the idea? Okay. So guys, with that as a fundamental understanding of precipitation reactions, we're now going to play with one on our own. We need to remember subscripts. Do you remember the subscripts in chemical equations? There are 4. They tell us the phase. So S is solid, L is liquid, G is gas, and then what is dissolved in water mean? AQ. Now guys, watch. Don't write this down in your notes, but I want to present you with something challenging, but then going to become wildly important. Now, don't write this down. What does that look like? What does it look like? But when you see this, what do you got? The stuff you put on your food, right? Sodium chloride as a solid. What does that look like? You've never seen it. Because guys, in order to get sodium chloride to melt, you have to heat it up to about 1800 Celsius. Imagine getting a saucepan, filling it up with table salt, putting it on your stove, and getting the salt to melt. You can't do it. Can you with sugar? Yeah, why can you melt sugar and not salt? When you're melting sugar, what are you breaking? The intermolecular forces. When you melt salt, what are you breaking? The ionic bonds. You can't do it, right? Now, guys, so this is the salt in your shaker. This you've never seen. This is salt melted, right? Not yet. What is this? Salt water. Guys, you ready for a disturbing thought? This doesn't exist. There is no such thing as salt water. You have never seen salt water. You have never tasted salt water. You have never made salt water. You have never touched salt water. There is no such thing as salt water. That's it. Guys, what there actually is such thing as is a solution of sodium and chloride ions. But there is no such thing as salt water. This is a complete misnomer. You cannot have salt water because the moment the water goes into the salt, it dissociates into ions as a strong electrolyte, and it is no longer salt water. It is sodium ion water, and it is chloride water, but there's no such thing as salt water. So you ready for this? What does salt taste like? You have no idea. You've never tasted salt. What you have tasted is sodium ion and chloride ion, because when you put it on your tongue is wet. And the salt dissolves into your saliva, and then you can taste it. We don't know what salt tastes like. There's no way to taste salt. Yeah.
So can we not taste anything insoluble?
No, because even things that don't dissolve, your tongue can still detect. Like fats don't dissolve in water, but you know the taste of fats, right? So like butter. You know what butter tastes like, but butter doesn't dissolve in water. But you've never tasted something that is a strong electrolyte in its complete form. It's always dissolved in water. Do you get the idea? Okay, so why do we care? Go ahead.
So, just a quick question. Does that mean that the sodium and the chlorine taste the same to us?
No, they actually don't. And so when we taste sodium chloride, the thing that you are associating with the taste of salt is actually the sodium. Yeah, interesting, right? Yeah. Okay, so guys, why do we care about this? Do this with me. Do not write this down, but read it with me. 1 molar lead nitrate solution is reacting with 0.5 molar potassium iodide solution. Guys, we're gonna tear this up. This is all we're doing for the rest of the day. We're gonna tear this apart, but it's gonna be really important that you do this with me. And here's what you need. You need 10 uninterrupted lines on your page. So if you're near the bottom of the page and you ain't got 10, you're going to want to flip over. Better to err on the side of more rather than less. So guys, at the top of your uninterrupted space, here's what we're going to do. We are going to write the balanced equation for this reaction. Guys, please make it as wide as your page, one line tall, but as wide as your page. Do it now. Write the balanced equation for this reaction in your notes. Hey, are you looking for paper? Oh, wait. Here you go, buddy. It's pretty heavy. You got it? You got this, man. You're all over it. Thank you. Thank you. Keep writing. I'm so glad. Thank you. Yes. See you, buddy. Yeah. You just get to know folks. That's seriously your brother? No way. Makes me happy. Yeah. Oh, goodness. All right, guys, let's play. You ready? We got brilliance in the room. Here we go. So, guys, we're going to write a balanced equation. There's going to be a lot of further steps, but let's do this together. You should be done. So, lead 2 nitrate. Yeah? Lead 2. You look up lead on the periodic table. It's 2 or 4. We picked the 2 because of the Roman numeral. Then this is reacting with potassium iodide, which is Ki. Then, guys, double displacement reaction. Our products are PbI2 and KNO3. Right. But, guys, remember we write the formulas properly first by balancing charge. Lead is +2, iodine is -1, thus PbI2. Nitrates -1, potassium is +1, KNO3. Now we need to balance it. 1 lead, 2 nitrates, 1 nitrate. So we need a 2. 2 potassiums, 2 iodides, and that balances. You good? Okay, now guys, this is where the brain engages. Because now what we're going to do is we are going to put subscripts on these. Solid, liquid, gas, or aqueous. Say again what you just said. Yep. Guys, anything that has a molarity has got to be what? Aqueous. Because the molarity tells you how much of it is dissolved in water. So here's the beauty. You get on the AP test and you're like, crap, I don't remember if the nitrates are soluble. And you're going, really? I would never forget that. Wait until you sit down to the AP test. You'd be surprised what you forget. So you get onto the test and you're like, hey, yo, I don't remember if the nitrates are soluble. If it's got a molarity, you immediately know that it's soluble. Then, guys, potassium iodide, also soluble. Now you're thinking to yourself, they're being tricky. What kind of reaction is this going to be? Well, we've got salts reacting together, and one of two things is going to happen. Either nothing or a precipitation reaction. It's a precipitation reaction. Which one of the products is not our precipitate? Not our precipitate. KNO3, how do you know? Nitrates always dissolve in water. So what does that mean? The lead 2 iodide's got to be a solid. It's our precipitate. Are we good? Okay. Now, guys, here's what I'm going to do. And I wish there was a way I could do this digitally, but I can't. So humor me. We need more space. So we've got, I'm just going to have to rewrite it. PbNO3 2 plus 2 Ki in equilibrium with PbI2 plus KNO3. And where's my other 2? Here? Is that right? Okay, and then I've got aqueous, solid, and aqueous. Are we okay? Okay, now guys, here's what you're going to do. You are now going to skip down 6 lines. And beneath those 6 lines, you are going to draw, and don't do this until you see, you're going to draw 1, 2, and I'm going to make that a little bigger. 2 and 3 beakers. And then, guys, what you're going to do is put some water in your beakers. And now, gang, what I would like you to do, please, and please only do this, but what I would like you to do is please on the reactant side. So you get it, right? This beaker, product beaker, right? Because eventually, can you picture what we've actually done? We've taken a beaker of lead 2 nitrate solution. We've taken a beaker of potassium iodide solution and dumped them together. Okay, so here's what I want you to do. Please, in these 2 beakers, here and here, draw what is in those beakers, not including the water molecules. Do not include the water molecules, but what is in those beakers. What is in those beakers? You guys okay? Okay, so guys, potassium nitrate, PbNO32AQ. No such thing, right? In the same way that there's no nitrate aqueous. So what's in the beaker? What's in here? So we've got PB, oh golly. Oh, it's frozen. Oh, look, it made a P. So guys, in this beaker, we've got lead ions, lead plus 2 ions. Notice the way it's written, Pb2 plus. And what else is in the beaker? Yeah, NO3 ions. But how many? Yeah, because we're going to go with relative amounts. So guys, in that, and can you almost picture it? You've got these lead ions surrounded by water molecules, and you've got these nitrate ions surrounded by water molecules. That's what's inside a beaker of lead 2 nitrate solution. There is no lead 2 nitrate. It's ions, okay? Do you want to change your answer now and for what's in the second beaker? Go ahead and do it if you need. So now, guys, what is in this beaker? What's in there? Potassium plus and iodide minus. So, guys, we've got K's and we've got I's. But we are going to honor the stoichiometry of the reaction, so we're going to put 2. Good? Okay. Now, guys, forgive me, but I'm going to run out of space. So I'm going to erase the subscripts just so I can write a little bit closer. Okay. So now, guys, here's the trick. This used to say lead 2 nitrate and lead 2 nitrate aqueous and potassium iodide aqueous. And that's really not what's in there, is it? We see from the picture that that's not it. So guys, what we're going to do now is we're going to rewrite this balanced equation to honor what is actually in those beakers. So guys, what are we going to do? Well, here on the left, we actually have this, don't we? We have lead ions. And what else do we have? 2 nitrate ions. And we have 2 potassium ions, and we have 2 iodide ions. Do you see what we've just done? We just took the reactants and wrote them as they actually exist. Guys, we'll come back to this term in a minute, but what we're in the process of writing is what is called a complete ionic equation. Breaking the things into ions so we know what the pieces and the parts are. Guys, what we're in the process of writing is what is called a complete ionic equation. Now, guys, to finish this process, here's what I want you to do. Go down to the right-hand beaker and draw what's in there. Actually, you know what? Let's don't, because, well, are you writing in pencil? Because you're going to have to, you know what? Let's just do this efficiently, because I don't want you to have to erase. Let me give you a clean copy, but let's talk and then we'll do it together. So guys, I'll do this small. This is solid and this is aqueous, right? Yeah? Did I get that right? Yeah. So guys, let's deal with the solid part first. Where is the solid? It's the precipitate. It's on the bottom. So the accepted way to do this on the AP test is to put the I want to do it in black. Guys, the accepted way to do this is to put the precipitate on the bottom. So PbI2, and then you draw a circle over it, a half circle, to indicate that is sitting on the bottom. That is your precipitate. Yeah. The half circle indicates that it's a pile. Yep, which makes it the precipitate. Now, guys, now that we've got that, you should be able to do the rest. Throw in your potassium nitrate into that beaker, because we've poured them all together. And guys, by the way, just so you know, I used to do this reaction like for my students. I used to actually bring in the beakers and dump them together. The problem is the lead is really hard to dispose of. It's a neurotoxin, and they don't want me dumping it down the drain anymore, and it's expensive to dispose of. I used to it's actually cool. You dump it together, and the lead 2 iodide is this really pretty yellow color, but we can't do it anymore. Okay, so guys, what about the potassium nitrates? What do you have in solution? 2 Ks, 2 NO3s. So we've got a K and a nitrate. Notice the charges. We've got a K and we've got a nitrate. So now that you've done that, go back up to your balanced equation, and now drawing in your yields arrow, write your products. Write on that line what is actually in these beakers. Okay, so what are we going to put for the lead 2 iodide? Lead 2 iodide. Guys, this is a precipitate. It is not broken apart. It's lead 2 iodide. Now what about our 2 potassium nitrates? 2 potassium ions and 2 nitrate ions. You okay? Okay. Now guys, here's the thing that's interesting. And again, you can picture this, right? You've got a beaker of this, you've got a beaker of this, you dump them together in the same beaker, and we now see the chemistry that they're doing. But here's the thing that's interesting. We have 4 different participants, right? We've got lead, nitrate, potassium, and iodide. But guys, I would propose to you that not all 4 of those species is doing chemistry. Some of them are just hanging out and watching stuff happen. Who's not doing chemistry? Well, let's talk potassium. So guys, check out potassium. Where did potassium start? As an ion dissolved in water. Where did potassium end up? As an ion dissolved in water. Potassium's just standing around picking its butt, letting everybody else do chemistry. So now guys, what about, is there anybody else here that's not doing chemistry? The nitrate. Where did the nitrate start out? In water, as an ion in water. Where did it end up? As an ion in water. It didn't do any chemistry. It's just sitting around doing nothing, twiddling its thumbs, not doing chemistry. Guys, who did the chemistry? Look at what, so lead started as an ion in solution. Did it end up as an ion in solution? No, it ended up in a pile, right? So guys, what about the iodine? Where did it start? Ion in solution. Where did it end up? Bonded together with the lead down in the pile. So guys, the lead and the iodine did chemistry. The potassium and the nitrate did not. And there's a name for that. Let's write this down. Guys, the name for that, and I guess we'll put it here. The name for this, the name for these in the plural are spectators. Spectators are substances in a reaction that don't do chemistry. So guys, do this with me, please. Neatly cross the spectators out of that equation. Lovingly, we're going to call this killing the spectators. So guys, kill the spectators. And then I'm going to share a deep thought with you. So is lead a spectator? No, it did chemistry. Is nitrate a spectator? Gone. Cross it off from both sides. Is potassium a spectator, or did it do chemistry? Spectator. So we're going to cross that out. What about the iodide? Did it do chemistry? Yeah. Now guys, check this out. Ready for a deep thought? Look carefully at the spectators. Nitrate and potassium. Now go back to the conversation we had 15 minutes ago about table 4.1. Do you see the connection? What's the connection? They are substances that tend to always be soluble. Nitrate always dissolves in water. It will always be a spectator. You will never have nitrate precipitate, and that's what the chemistry doers did, right, is precipitate. Nitrate will always be a spectator because it doesn't like to grab a hold of things and not dissolve in water. What about potassium? Where does that fit in? It's a group 1 metal. Those are also salts that tend to be soluble in water, so that is also a spectator. So guys, when you're looking for spectators, look for substances that you know tend to be soluble. So now here's what we're going to do. We are going to now go down here and we are going to pull the spectators out of our beakers. And now, guys, we can finally get to the representation that is simply of the chemistry that took place. So, guys, when we mix these two solutions together, functionally what we did is this. We took lead 2+ ions and we reacted them with 2 iodide ions, and when we did, we formed a lead 2 iodide salt. What's that?
So which one's the complete ionic?
Let's talk, that's just one moment. That's what I want to do next. And it's cool that you picked up on this probably from summarizing the chapter. Guys, what we have just done, and do you understand that this now represents the chemistry that actually took place? Okay, guys, what we have actually done is written 3 different forms of a chemical reaction. This is the one, the top one is the one that you walked into this room knowing from last year. Guys, this has a name. I don't know. All right. Violet. This is what is called the complete molecular equation. The top one is what is called the complete molecular equation. That is the way you learned to do this last year. Guys, the second one is what is called the complete ionic equation. Notice complete means contains everything. So the complete molecular represents everything together. The complete ionic represents the strong, oh, catch this. The complete ionic represents the strong electrolytes broken into their ions. Chew on that for a minute. The complete ionic represents the strong electrolytes broken up as ions. What are strong electrolytes? Things that break apart completely, right? So all we do is we take the complete molecular, break the things that are strong electrolytes into their ions. Notice that we did not break apart the lead 2 iodide because it doesn't break apart. It's a precipitate, it's non-soluble. Then guys, at that point, we killed the spectators. And what did we say the spectators were? The things that don't change. The things that are always soluble. And at that point, guys, we got down here to what is called the net ionic equation. I'm gonna have you wait for a second, Justin. So guys, let's talk about net ionic equations and then we'll answer questions. So here's the deal. From here on, you will only write net ionic equations for chemical reactions on the AP test. They will have you only write net ionic equations for chemical reactions. So let's talk about some of the things you need to understand. First of all, net ionic equations never include subscripts. You'll never put aqueous and aqueous in solid. So guys, let's talk about why. Why do I not need to put aqueous down there? No, because it's an ion. Guys, the only place that lead is an ion is when it's dissolved in water. So if you have a substance that has a charge, as an ion, if you have a substance that is a charged ion, it has to be in water. If it's not stable. And so when it says a charge, that begs that it's aqueous. So we don't put subscripts because it's unnecessary, because the charge tells us it's dissolved in water. And we can see that. This is dissolved in water, and these are dissolved in water. Then why don't we put solid on this? And the answer is because the assumption is that we all know the solubility rules and we know that it's a solid. Yeah.
But what if it's
then there would have to be something special in the problem that says, oh, by the way, this is at 1800 Celsius, and at that point water couldn't exist, and then the game's completely off. So yeah, so when we talk about aqueous chemistry, we tend to limit ourselves to room temperature. So go ahead, Mark. Yeah, so that's interesting, right? Because if you look at a combustion reaction, and I'm not even going to balance it, but if you look at the combustion reaction, that's the complete molecular equation and the net ionic equation and the complete ionic. It's the same because this doesn't happen in water. So the only place that we are writing net ionic equations is for aqueous chemistry. Is that okay? Okay. So guys, with that said then, going back to this is the take home for today. When we write aqueous chemistry, and you're going to find out this is acids and bases and redox and all of that, guys, we will write net ionic equations. And so you need to develop the skill of writing these, hopefully without having to draw all the beakers. That's the challenge, and that's what you're going to see in homework. So, guys, with this said, let's get rid of this, click here, do this, go here, do this. So guys, don't write these down, but if you would like, here is the definition of complete molecular, complete ionic, spectator ions, and net ionic. But I think what you have in your notes is even more valuable than these words. And then guys, here's your homework. Now you know what you need to know to answer all of these, and we will grade these on Thursday. We now have about 15 minutes for us to, before we're done. So guys, the expectation is the next 15 minutes are going to be spent picking up where you left off in the homework, starting to work through these. Guys, we will address these on Thursday, and then we're going to look at acid-base chemistry on Thursday. Just a second. Go ahead, Mark.